In the last video, I introduced to you this other kind of estimation approximation technique in approximating some definite integrals that we don't know how to evaluate, and that was just through proving an inequality by finding an easier to evaluate definite integral. And in this video, I want you to get some more practice with that and work on another problem. So I want you to again find another easier to evaluate definite integral that proves this inequality here. So pause the video and give that a try on your own. All right, assuming that you've given it a go, just looking at this definite integral over here that we're trying to prove an inequality with, we have the definite integral from 0 to 1 of e to the negative x squared power. And that is a definite integral that we don't have tools to solve right now. We don't have tools for that. And just real quick, just a little side note, a little tangent. This is part of the error function, and that's widely used in probability. So playing around with this type of integral is very important in some domains, especially probability. So we're going to get some practice with figuring out, okay, is this greater than 1/2? We're going to figure that out in this video. So again, we need to find an easier to evaluate definite integral. And looking at this integral over here, I see an e to the negative x squared, and I'm trying to think, okay, I don't know about you, but I love taking the integral of e to the x. And if I could get something close to that, that is what we're after. So what if we were to try something like this? Let's try a definite integral like this. Definite integral from 0 to 1 of e to the negative x power dx. This we know how to solve. When we integrate this, we get the following. When we anti-differentiate e to the negative x, we get negative e to the negative x power, and then we're going to be evaluating from 0 to 1. So we know how to solve this. We know how to get a value out of this definite integral. But now the question is, okay, is this valid to help us prove this inequality? And like in the last video, we need to compare these two definite integrals. So we can rewrite them over here, dx, and we can look at our easier to evaluate definite integral as well, e to the negative x dx. And now we're trying to figure out, okay, which one is greater than the other one, and what are we ultimately hoping for? Well, if we want to use this definite integral to even talk about, okay, maybe it could help us prove this inequality, well, it needs to be less than this integral in orange. So let's see if that's the case. And how do we do that? Well, in the last video, we saw, okay, we can pull out these integrands, look at these functions over an interval, and if we can prove that one function's greater than or less than the other function, well, then we can say that the definite integrals of those functions are greater than or less than the other one. And again, we interpret that as area under the curve. So let's see here. Let's pull out these integrands and look at them. So we have e to the negative x and e to the negative x squared. And what interval are we interested in comparing these guys? Well, we have the same limits of integration. So we're looking from 0 to 1. We're looking at from 0 to 1. And are we including these endpoints? If we ultimately want a strict inequality, do we include these endpoints? Well, no, because when we plug in both of these endpoints here, we get the same value. So if we want a strict inequality, we will not be including these endpoints. So we'll look at values between 0 and 1. And again, we saw in the last video, we can just continue to whittle these functions down and continue to look at their parts to establish an inequality. So we can just rewrite these guys a few times, and then we can pull some parts out. So we can then look at e to the x, and we can look at e to the x squared. And then we can also go one step further and look at x and look at x squared. And then on this interval between 0 and 1, we find that x is actually greater than x squared. And then when we exponentiate that value, we're going to get the same inequality there. And then when we go 1 over that value, this inequality is going to flip. And then again, this line right above it is just rewriting it, so we get the same. And then we ultimately get the same for our definite integrals. And again, you can interpret these as area under the curve. Although these functions start and end at the same values, we've just proven that one function is going to be greater than the other one throughout this interval. So we can say that the areas under the curve of these two curves one will be greater than the other one, and that's what we've proven here. So now that we've established this and we got the result that we were hoping for, we found an integral that was easier to evaluate, that was less than this other integral. Now we need to decide, okay, is this enough to prove our inequality? Is this enough to prove this inequality up here? So we now need to figure out, okay, is the value of this integral enough to prove that this definite integral is greater than 1/2? And really, let's ask ourselves, okay, what kind of value are we hoping for here? If we get a value out of this definite integral greater than 1/2, is that enough to prove this inequality? So if we get something like 0.6, is that enough to prove this inequality? Well, yes, that is. But conversely, if we got something less than 1/2, something less than 1/2, like 0.4, this definite integral could take on values from 0.4 up to 1/2, and that would be not enough to prove this inequality. So we're really hoping for a value out of this definite integral to be greater than 1/2. So let's see if that's the case. So let's evaluate. We have negative e to the negative 1 power minus negative e to the 0 power. And then we get, let's see here, negative 1 over e, and then we have plus 1. So we can maybe rewrite that, 1 minus 1 over e. And now we need to really consider, okay, is 1 over e, how does that relate to 1/2? Well, e is roughly 2.718. So this is going to be roughly 1 over 2.718. And how does that relate to 1/2? Well, I mean, this is closer to 1/3 than it is 1/2, so it's going to be less than 1/2. And then when we come up here, we can see that 1 minus 1 over e is going to be greater than 1/2. So that's exactly what we wanted. We wanted a value greater than 1/2, and we've just proven that that's the case. So what we did, we found a definite integral, this one right here, that was easier to evaluate, that allowed us to prove this inequality, and we're done.